I'm going to talk about the sustainability in high-rise buildings with respect to the structural system. Now, if you told me to do that a few years ago, I would probably say that I only need 5 minutes to do it, and I'll be done. So let's see how I'm going to be doing it today. So I'll start with some early green projects that we at WSP engineered. So back in 1999, 4 Times Square was completed, a 48-story steel frame and concrete structure. It was the first green environmentally responsible building in New York City. Many of the now known LEED guidelines were established during the design of this building. Just to name a few, limited the radius of material delivery to 100 miles. The use of fly ash was introduced in the concrete mixes, and something as obvious as electronic shop drawings was introduced back then. The Solaire was the first sustainable residential tower in New York City. It's completed in 2003. Some of the sustainable aspects that were implemented in these buildings were very unique to those days, like black water recycling, using solar panels for electricity. The Health Tower, very unique structure located on 57 Broadway in New York City. It's a 46-story steel tower. Achieved a LEED Platinum certificate. Together with the architect, we went through various iterations of how the building is going to look like. At the end, the architect fell in love with this nice diagrid system, which ultimately saved about 20% in steel as compared to a typical office building. Okay, at the World Trade Center site, one of the main goals was to certify all the new buildings to be LEED Gold. As such, 7 World Trade Center, the first to be built after 9/11, received the LEED Gold certificate. It's a 52-story steel frame and a concrete core, 230 meters tall. Following 7 World Trade Center, 1 World Trade Center will receive the LEED Gold certificate soon. It's 102-story steel frame and a concrete core, 541 meters, one of the tallest buildings in the world. Okay, so at WSP we take sustainability very seriously. So even though 56 Leonard was not designed with sustainability as a specific goal, so you won't find any solar panels on this building. So we adopted many of the characteristics of sustainability with respect to the structural design. So before we begin, when you start a new project, you have to decide what material you're going to use. Is it going to be steel? Is it going to be concrete? So back in the day, at the beginning of the modern era of construction, steel was exclusively used since concrete was lacking strength and low modulus of elasticity. However, in the last 2 decades, achievements in high-strength concrete together with environmentally responsible materials were made, and concrete became popular. And today, most of the tall buildings are built using concrete as the base material. Some of the advantages, you get the higher inherent damping, which is very important when you design a tall building. Specifically in New York, it's easier to build residential buildings. It makes more sense. You can make changes right close to the construction, and so on. So we went through many different schemes. Some, because you can see this is not a typical regular building, too many cantilevers, I would say. So we went through many different schemes. Some were structural steel alone with precast cladding, some hybrid of portions of the building structural steel, portions concrete, some concrete core with structural steel. At the end, it made sense from a cost perspective to do it out of concrete throughout. So it's a 57-story concrete structure, 251 meters, and it's under construction right now. It's expected to be topped out around September 2015. And you can see the nice cantilevers they have. So as we all know, land is scarce. We're lacking land. Sites are getting smaller and smaller and very expensive. The cost of land is on the rise. And so as such, this building, the owner tried to maximize as much as they can the height on a smaller footprint. The height of the building is 250 meters. With a width of about 24 meters, you get a slenderness ratio of about 10.5. As you all know, above 7 is a slender building where the engineer needs to take some tension. The building will consume about 29,000 cubic meters of concrete and 4,500 tons of steel. Okay, so now we'll go into the sustainable design. We believe that wherever we can be environmentally conscious, we should, even if it's a small fraction of sustainability, we will go for it. As such, when we went to the site at the first, when we just got the job from the client, we went to the site, we saw that there are some existing walls that they were suitable for use, and we decided to keep them. Some engineers would say, why do I need the headache? Let's remove them and build a new wall. We took the other way. We saved on the demolition and the waste disposal. We saved on the construction time. We saved about $700,000 in support of excavation and foundation construction costs. Clients, they love it. You save them money. So it's a good initiative. The use of slag and fly ash in the concrete mixes. So fly ash and slag, byproducts of coal combustion and ore production. You can see on the pie chart the cementitious mixes that we had on this building. Cement is only 35%. Byproducts are 65%, which is pretty good. They added, other than using environmentally friendly material, you get the rebar protection, reduced water cement ratio, reduced heat of hydration, especially when you have mass concrete, it's important, and increased high strength. Some other added benefits would be low permeability. Happen to be that 56 Leonard is also actually exposed concrete, so low permeability is an advantage. Okay, computer finite element analysis, what do I mean by that? We are very passionate, all engineers are, and we believe that we should do whatever it takes to create the best and innovative, best new thing. So we used a computer finite element programs and some in-house spreadsheets to design some very unique conditions that I will just quickly go through. That eventually, the bottom line is that we saved that on material and we're being cost effective. So at the 5th and 6th floor, the architect had the idea of having this nice cantilever projecting out. It's about 8 meters. We used the 3D analysis, as you can see over here. What we did, we created sort of a Virandel truss, a concrete Virandel truss. where we engage the 5th and the 6th floor via a vertical concrete column. You can see here on the picture that it's built, it's standing, no deflections, no overstresses, looks pretty neat. On the 7th floor, we had this cantilever terrace. We had the pool at the 7th floor. And as you come out of the pool, you have this nice terrace that is overhanging the adjacent building. It's located right over here. What we did, the concept we had is to extend the pool slab with the terrace slab and engage it with concrete walls to create some sort of an I section on a series of I sections. So as you all know, I sections are very efficient, and it proved to be very efficient and cost effective, and we saved on some unnecessary material usage. So I hope that by now you kind of figured what type of building we are dealing with. It's a very unique building. On a typical residential building in New York City, you would see probably, if we compare a 60-story building, you'll have maybe 10 different floor plates. This one had 57 different floor plates, and we had to go through them all. It was painful, but we did it. We utilized the finite element program, whatever was back at the day that we could use. As you can see on the plan, the balconies were dancing around the perimeter of the building, and to accommodate the different architectural layouts, columns had to also be relocated from floor to floor. So to relocate the columns, we utilize what we call a walking column concept, where the column from above and the column from below are tied through a 1 to 2 story concrete wall. The eccentricity that's between the column above and the column below was resolved with a lateral force at the top and the bottom of the wall, and through the slab to the core that was taking that lateral force. Okay, so we used the highest concrete strength that was available to us back then, 83 megapascal. By using the high strength concrete, we minimized the sizes of the shear walls and the columns, and by doing that we saved on the material. The lateral system was utilizing the 32nd and the 46th floor, which are the mechanical floors. We utilized them as outrigger floors. So we created sort of a concrete belt around the perimeter of the building, engaging basically all the exterior columns and to participate with the lateral system. We had 2 outriggers in each direction, engaging the belt into the core. This by itself increased the rigidity of the building by about 20%. Okay, so 47th floor to the 57th floor are basically very unique concept that the architect had, the Herzog and de Meuron from Switzerland. They felt that that they should have a stack of homes, independent homes, one on top of the other, create sort of like a sky home in the sky. You buy your own house in the suburbs. The only difference is that you're going to live 200 feet above the ground. Each of those floors had a different layout completely. we had to come with whatever we had on that. We used the same Virendel truss concept, some cantilevered walls coming off the core, and 85 centimeter deep beams were framing the floor slab, since almost none of the columns were either going down or going up, so we either had to pick them up or hang them from the floor above. So if I go 10 years ago or a few years ago, it would probably be very difficult to design something like that. The advantage of having a computer finite element program is that you can design it today and get a very efficient system. I guess you can imagine how complex this would be just to coordinate with the mechanical engineer. As a matter of fact, we are on the 52nd floor doing coordination with the mechanical trades. It's been painful. A few more floors to go. I hope we'll get it soon. So the last point, which somehow tied into the concept of the workshop today, is the damping system. As you all can imagine, when you have a tall and slender building such as this, you have to go to a wind tunnel test, because the client who buys this unique apartment, you don't want him to feel uncomfortable living sort of like in a boat on a rocky boat. So we went to the wind tunnel test. I'll just go through it quickly. Acceleration criteria for residential buildings, 15 to 18 milli-G over a 10-year period. The office buildings, 20 to 25 milli-G. Now, when we submitted the properties to RWDI, the wind tunnel testing lab, first properties we submitted, and with the inherent damping of the structure, we got this result, 25 milli-G, which is above the industry standard. So we asked them to perform a sensitivity analysis and see what the damping ratio, total damping ratio that is required to get this building down to the acceptable acceleration limits. They came back with a 3.5% damping ratio. So since it's 3.5% damping ratio, we decided to go with a liquid tune damper. We placed it nicely at the top of the building, just above the main roof and the bulkhead. The concept of the damper is very similar to the mass tune damper. The only difference is that the mass tune damper has a pendulum, and this one has the water to counteract the movement of the building. There are 9 pedals, sort of like a grid of a 3x3, placed in the damper. The size of the damper is about 10 meters by 10 meters by 3 meter high. Contains about 150 cubic meters of liquid of water. It could be recycled water. They can also have the option to use this as a fire protection water tank. When this building was designed in 2007, not too many buildings in New York had dampers. So we got sort of a push from the marketing people about using a damper. Their logic was that if a client comes in and they finds out that there is a big pool at the roof, he will ask, what's the purpose of that pool? And then we will say, oh, it's to control the movement of the building. And he says, oh, the building is moving? That doesn't sound good to me. So it wasn't a good selling point. So what we did some additional studies to see what would the structure require not to have a damper. And we found that we would probably have to add about 15% in shear wall and column sizes and reinforcement. which translates, after deducting the cost of the dumper, to about $1 million. So the numbers made it, and today happened to be that this site was stalled during the financial crisis. But when it restarted, more and more projects are using today damper, so it's more a common practice, if you can say. Basically, I'm pretty much close to the end. Just to summarize quickly, if there is a will, there is a way. And anything counts where it comes to the environment. Using of computer programs, finite element programs is saving in material. The use of slag and fly ash is very common these days. We have some projects in the city that we are using high-strength concrete, more than 83 megapascal. We're getting to 96 megapascal these days, and the concrete breaks are coming perfectly, no issues. I haven't had any low breaks on the other buildings that I'm doing right now, the 432 Park and 99 Church. And the last one is the liquid tune damper. It's for human comfort, but also saving on material, and could be cost effective when designing a slender building such as this one. You can see here the windows installed already.